All right. So the next talk is about is from Georget. Sorry, by Georget. It's titled "Using a Hardware Signal to Detect Malware in Critical Embedded Systems." Luca is currently a PhD student and working in between one company, EDF R&D, so en français, and LAAS-CNRS lab once again. The floor is yours.
Thank you very much. So, hello everyone. It's a real pleasure to present once again at the Toulouse Hacking Convention, this time for the 10 years of the conference. So, as Benoit said, I will present a hardware signal extraction method to detect malware in industrial systems. So, this was joint work with Vincent, Philippe, Arthur, and Frédéric, and it was accepted recently at the IOLTS conference. Okay, for the context, so we are in industrial control system, which is operational technology. So at the left, you have the classic corporate network, the IT one, which is separated from the industrial control systems. Industrial control systems are split in two parts. The supervision, so the SCADA one, with like a console and screen for operators to see what's happening into the production network. Some maintenance stuff, and for example, the data historian to keep the data. And the production network, where Case presented some wireless technology that could be there, but also we are focusing on programmable logic controllers that will collect data from sensors, and also it's a control command system, so they will pilot actuators, sometimes through a workstation, and this is what we want to study. So our threat model will be supply chain attack with Trojans. So if a cyber attacker crafts a malware that is mimicking a legitimate behavior of a programmable logic controller, it could send it to, if it's an employee, to a third-party software vendor, and this Trojanous software will go into our industrial control system, into the programmable logic controller. And above, if we give a focus more on the product side, you can see that when you will have some updates, for example, of a correct product, it could be corrupted, and you can even change the software, the libraries, or the low-level firmware, and this is where we want to focus. So our goal is to detect and even, if we can classify the malicious variations that an attacker could do into the programmable logic controller. And so, such as we are targeting low-level software, such as the firmware, we have classic software countermeasures could not work. So we are looking at the microarchitectural layer. Current state-of-the-art focus a lot of hardware performance counters because they are already implemented into the CPUs and easily extractable from that with some software methods. If you use a perf in Linux, you will get them. And we wanted to craft an alternative with security on, with a focus on security and not on performance. So how we did that, we followed our methodology. So first you have to target a specific hardware architecture. If you target embedded system, you can use a CPU like the VEX RISC-V, or if you want a more complex one, you can go into the CVA6, for example. After, when you choose the CPU you want to use, you can compile some software programs to benchmark even the legitimate program and the variations you can do. Once you have your software, you can try to select which metric into the microarchitecture you want to extract. So in our cases, we extracted the communication buses of a system on chip. And you will craft some features according to these signals that you capture to have the custom counters made for security. In our case, we extracted the instruction, the addresses, the memory addresses, and the control signals. We format them into counters, and we give that to a machine learning algorithm. we let it process, and at the end, we can have an hardware detection module with simple thresholds to re-implement into the device that will go in production. All of this could be done first in a test phase. Okay, so to extract microarchitectural signals, we have to probe the microarchitecture. So we use an integrated logic analyzer into an FPGA chip. So this is a generic approach. You have your CPU. It will expose some signals to communicate with the rest of the system on chip. For example, after the instruction and data caches, you can, with a framework that I will present, extract some signals. Here it's a wishbone bus, but you can do whatever bus technology you want, AXI, AXI Lite, as you wish. There are some control signals, like to do handshake with this bus technology, strobe, seek, acknowledge. So this is signals on 1 bit, so you can easily say if it's up or down. But for larger signal, like the one on 32 bits, you have to split them into categories. So for the RISC-V instruction, we looked at the 7 last bits of the signal, depending who depicts the outcode. And based on the RISC-V specification, you have this opcode map where you have all the categories, and you can see which category was currently happening. When we went to the CVA6 CPU, it was also allowing compressing instruction. So there is a second opcode map to use, but I didn't put it in the slide. It will be too enough. Okay, and for the data part, we wanted to see which addresses were accessed, because it will give us like how many interaction the CPU has with the rest of the memories of the system on chip. So you can check the memories you used into the system on chip, a ROM, a RAM, a SRAM, and you have also the control and status registers with all the peripherals you can use, if you have LEDs, if you have UART, if you have Ethernet, things like that. Okay. Go back to the industrial context. So we wanted to focus into a programmable logic controller. So we had an FPGA board. We connected through UART to a NOST PC that will be like the supervision room with a screen. We extracted signals through Ethernet to a NOST computer that will process the data afterward. Because in hardware we work a lot with the LEDs to see if it's working or not, we had the LEDs to indicate the current status of the device, and we also had some P modes to have an ambient light sensor to give us like the current luminosity of the room. And for all of that, we use the framework LightX, which is very convenient to build the system on chip. So just a quick words about LightX. Once you have an FPGA toolchain into your computer, either an open source one or a proprietary one like Vivado or Quartus, and an FPGA board, you can choose whatever hardware layer you want to put on it. Choose the RISC-V core that are already implemented into the framework. If you have some own custom digital design, you can add it. And you choose the peripherals, and it will automatically compile a Verilog file that you can use to program the FPGA with all the connectivity, so it's very convenient. And on top of that, you have also additional tools to craft custom firmware. If you want interrupt and schedule mechanism or not, if you want to avoid them. For example, you can have some real-time constraint operating system. If we talk about industrial device, you can run C or C++ code on top of that. You choose whatever you want to do. Okay, our firmware corruptions will be studied according custom bare metal BIOS that is doing the following steps. Okay, we start the program. There is a trigger instruction for our integrated logic analyzer. We get the sensor data, so the current luminosity of the room. And according to this value, if it's too low, too high, or between correct values, it will print an associated state message, set the LAAS, as I said, to a certain value. And if it's too low or too high, it will raise an alarm to the operating room. And we, at these 3 different layers, we crafted some illegitimate deviations, switching, for example, the associating message or faking the value of the sensor that is going into its supervision. And once you boot the simile programmable logic controller, you will have this available commands with the legitimate one and malicious ones. All of that, as I said, we give that to machine learning algorithm. We could start with some clustering to see some abnormal data. And after, we use the XGBoost and the decision tree mechanism to classify the legitimate program and the variations. So it gives us good results. We had 2 types of counters. I think I will be quick. I will not detail that. But you see, if you have only the instruction part or only the data part, there are some confusions that are left. But by combining the 2 of them, it's increased the accuracy. And at last, we wanted to compare our work to the hardware performance counters from the state of the art. And on the CVX6, we got better results than them. So XGBoost can give us more knowledge about the microarchitectural behavior of the device. As I said with the tab, on the matrices on the left, there are some programs confused because we took only the instruction part and on the matrix of the right, only the data. And it's not the same program. So by merging these 2 metrics, we can have a great hardware detection module. And on the right, XGBoost could show you like the most relevant features that it's used for classification. So for example, if we take only the fourth one, on the data bus, you have a byte selector to see which byte you will look in the data that is going through the bus. So this is very relevant to classify the according programs. There is also a strobe and write enable control signals and the number of access of the main RAM. And all of that, you can put that into the decision tree with according thresholds. And it will classify your programs and you can embed this once again in the device to go to production afterwards. So this is the end. I'm currently working on hardware trojans because it was like software corruption, and now I want to address hardware ones. And I will just take 1 minute to thank many people that helped me through all of that. So like 9 years ago, Christian brought me to the first edition to the Toulouse Hacking Convention, and since now I'm continuing on that. Benoit helped me for the Lightix framework, Philippe for the machine learning stuffs. Aurélien helped me spend a good time in Eurocom in double diploma. And Vincent, of course, for supervising both my internship and my PhD studies, and all the colleagues in EDF, because it was 3 years very cool there. And if you have any question and are angry, it's time.
Thank you. Question or lunch? No, question. Yes.
Yeah, thank you for the talk. I have a simple question. When you use the learning for training your system, how do you ensure you are training it on softwares that are not malicious, and then avoid not detecting what should be?
Okay. If I understood correctly the question, in this case, we crafted both the legitimate software and the malicious variations. So it's kind of pre-shooting the possible attacks, small ones, that could happen on the device, and has the safety methods to detect some failures. And in the learning phase, we mixed equally both a legitimate approach and attack methods. And this is what you can see like on the matrices. There is the O1, which is the original, and all the other ones are like illegitimate variations.
Thank you.
Hello. I have many questions, but I will focus on one. So I'm not sure to understand about the configuration on the hardware detection part. Is it a configuration that you uploaded later, or is it part of the production process of the hardware? So in case of an update, you have to update your detection thresholds, I suppose. So how does all of that mix together with the update mechanism?
Okay, yeah, I understand the question. Yeah, it's not classic hardware development phase, as the assumption is that we can have one device to test with a specific firmware on it. We could incorporate our integrated logic analyzer, extract the signals, run some tests, and then craft the detection module that we want to embed after for production. But of course, if you change the firmware, if you change the architecture description, you will need to go again into this cycle and recraft with new thresholds, etc. So yeah, it's a little bit hard to how could I say that? For an industrial, it's hard to force a supplier to respect all of this hardware design phase. So, yeah, but I think we can discuss that at the lunch.
Not lunch. More questions, sorry. Frédéric. Thank you for the talk. 99.7% of accuracy is really nice, but as we've seen during the first keynote, that's still 0.3% of false positive, which depends on how many entries you have, but it can be a lot. Do you have an idea on how to, what you do with these false positives?
Yeah. This is a very big problem into industry, like the number of false positive that goes to a security operations center. One of the methods that you can use, it is a determinism mechanism that will have a cyclic periodic execution of programs. You can try to see if you have one alert raise, then if the next cycle will also be an alert, and according to a threshold that you can put, finally send the alarm. But also what I want to highlight is that the percentage we have there is to classify malicious variations. So it's not about detection. Detection, it's almost perfect, because when you can see like the original program, we have all of them not confused. But when we want to say, additionally to the detection message, okay, we think that the variations could be this kind of failure, this is where sometimes we have some confusion.
Last one.
So as you just said, due to the nature of the code running in these PLCs, which are typically cyclic executions of code, which is basically, to make it simple, a state machine, right? You try to model and see differences between state machines. So why use machine learning? I know it's hype these days. Everybody wants to do that, but isn't that an overkill? Isn't there a much simpler way to represent these state machines and see differences in them?
Maybe. I'm not an expert in this field. We wanted to have machine learning because we wanted to extract like a lot of microarchitectural signals and then see which were the most relevant ones. Maybe with some final state machine methods we could have a similar results. It will be to try, but I think for the next one, because I'm at the end of
PhD. Maybe you start another one.
Maybe.
Okay, thank you. I think this is the last one, so enjoy your lunch. If the speakers of the beginning of the afternoon are here, please come and see us for your presentation.